1/4 of a unit. Now you're out here along the y-axis, but that doesn't show when you're projecting on the xz plane. So projection of the xz plane is here. When t equals 1, then t squared k is 1, so you're up here at 1 unit on the z-axis. When t is 3/2, d square 3/2 is 9/4, a little over 2, so that puts you up here. And when t equals 2, which I didn't label, put that in there. When t equals 2, your projection onto the xz plane is at the point 1, 4. Cosine of pi t is back to 1. T squared is, t is 2, so t squared is 4. So the z component, or the k component, is 2. So you have this, and of course you know you're going around the circle as you do this. So what happens is you're going around the circle, and you don't go up much by the time you get out to the y-axis. But then you go up some by the time you're at the negative x-axis, -1 on the x-axis, and then you're up even more than that by the time you're here, and then you're back to the x-axis. So you've got something that increases faster and faster. So this shows you how the coils of the helix get spaced out more and more. Unlike the picture I had previously. In the picture I had previously, and if it was on the board behind here, I'd look at it, but I don't want to do that. But you recall, we went around the helix, and we ended up going up at a constant speed, and by the time we got around one cycle in the xy plane, we were up 2 units. Here, so that picture, by contrast, would look like this. We're at 1/2 a unit, we're at 1 unit, we're at 1.5 units, we're at 2 units. So in that picture, looking at those coils, that first coil from the side would look something like this. Now, in contrast, we have this upward curvature thing. The second coil would go out to t equals 4, so we'd be up 16 units. Now, if that's 4 units, then 16 units of 1, 2, 3 more of those. So we'd be all the way up here. So the second coil, or second time around this thing, we'd come around like this and end up way up here. The coils space out more and more. And that's what I've attempted to show here. This should be 4 times as high as this. It isn't. It's about 3 times. I didn't do a good picture. Should have been up here. First coil comes around like this. Second coil comes around like this. Now you got to think in 3 dimensions, the way the coils are turning. So all this is happening above the unit circle in the XY plane. Then if you have this picture goes with this down here. It just extends this picture to another cycle. Okay, down here we have cosine of pi t squared I plus a sine of pi t squared j plus tk. What happens here? We follow the same path as before, but we go around the circle faster and faster. Actually, we don't follow the same path as before. Anyhow, the cycles of the circle in the xy plane are completed as before when we had the t squared here in 1.4, 0.6, 0.45 time units. Okay, so we're going faster and faster around a helix. If you can imagine that motion like at an amusement park or something, it would be, it'd be kind of a fun ride, wouldn't it? Until you got going too fast. So, yeah, presumably you engineer the thing so it doesn't get going too fast. Okay. If we do the XZ picture of this thing, we go around one cycle in the first 2 seconds. So here's t equals 0, t equals 2, t equals, t equals, it's not 2 seconds, it's 1.4. Here t equals 2, and here t equals about 2.45, the numbers we had earlier. So we're going around the circle at the same time as we're going up. And we go up further in the first cycle than we do in the second because we're going up at a constant rate, tk. Now this rxz, probably bad notation, I used it down here. It just means the xz projection of our path. So we go up further during the first cycle than we do during the second cycle, and even further, and further in the second cycle than we do in the third cycle. So these points, further here, a little less distance here, and even less here. The cycles also take less time. So we have 1.4 seconds to go around the helix up to this point. We only have another 0.6 of a second to get around it to this point, and only 45 hundredths to get around to this point. So we're not going up as fast, but we're going around faster and faster. Okay, well, this is kind of a repeat of what I said earlier. For any path, t equals r prime over the magnitude of r prime. I didn't put the prime on it. Okay, magnitude of r prime. And that's a unit tangent vector. Then the normal vector, which is the rate of change of the unit tangent vector, which is perpendicular to the path, divided by the magnitude of that rate of change, and I did put the prime on that. Also curvature. I talked about this with a different picture up here, but if you're going around a curve, your unit tangent vector is going to change between 2 points. So if the curve is like this, unit tangent vector here will be maybe in this direction. Unit tangent vector a little further will be a little more in this direction. The difference will be in this direction back toward the center of the circle. For points separated by the same distance on the arc of a circle, the magnitude of the change in the unit tangent vector will always be the same, because the unit tangent vector is perpendicular to the radial vector, and the difference in the radial vector is always the same. Now you might have to digest that a little bit, or read a different explanation. But if you're moving on a circle where you keep speeding up, and look at the unit tangent vector at 2 different times, the points on the arc are not going to be separated by the same distance on the arc. Okay, well, the curvature doesn't depend on how fast you go around the circle. The circle has its own curvature. The faster you go around the circle, the faster t prime is going to change. The faster t is going to change. In other words, the greater the value of t prime. You compensate for the fact that if you're going faster on the circle, t prime is going to be bigger for the same 2 points. And you compensate by dividing by how fast you're moving. Okay, so that's the rate at which t is changing in time. That's the rate in which your distance along the arc is changing in time. And if you divide it out, you get the rate at which the unit tangent vector is changing with respect to distance along the arc. And that's what we call curvature. I gave a better explanation for that in class because I had a picture to refer to. Don't have that picture. And then there's one more picture that I no longer have because I had to clean it for another class. But I'll do a separate, shorter video showing how the unit tangent, unit normal, and binormal vector and acceleration vectors compare, because that's the subject of the upcoming assignment.